Hello everybody and welcome back. Root Beer here with the very last question on the 2008 Galois paper. So, if you haven't tried this question, I would encourage you to click the link in the description, download a copy of the contest for yourself, and try question 4. Always try question 4, even if it's the Friar, this is the Galois, or the Hypatia. They're the hardest questions, and they're the ones that are really intricate and usually have some very beautiful and interesting math behind them, but also are great for practicing your writing up skills. Okay? So as I say, it's Galois paper 2008, and we are on question 4. What have we got? So Carolyn and Paul are playing a game that starts with a list of the integers from 1 to n. The rules of the game are: Carolyn always has the first turn. Carolyn and Paul alternate turns. On each of her turns, Carolyn must remove one number from the list, such that this number has at least one positive divisor other than itself remaining on the list. So I don't think she can ever remove 1, because 1 has no other positive divisor other than itself. It's a unit. On each of his turns, so Carolyn removes a number, then Paul must remove from the list all of the positive divisors of the number that Carolyn just removed. Oh, so 1's going to be gone very, very quickly. And if Carolyn cannot remove any more numbers, then Paul removes the rest of the numbers. Here's a sample game just to make sure we're understanding it. So we've got 1, 2, 3, 4, 5, 6. Carolyn removes the 4, and that leaves these numbers. Paul removes the factors of 4 that are left, 1 and 2. That leaves 3, 5, and 6. Carolyn can't remove 3 or 5, because they're primes, and their only other factor, 1, is always gone on the first step. Prime numbers might be interesting here. In fact, we might have to count number of factors in some way. Just spitballing, because I don't know the actual question itself. But primes might be important. How many prime how many primes there are. Like 6 has 2 and 3, but so is 12, because 12 is 2 2s and a 3, and those are distinct prime factors would be 2 and 3. So a number of distinct prime factors might be important in some way. Just generating ideas as I read through these things, and I'm trying to verbalize them so that maybe someday you make those connections too. So Paul removes the 1 and 2, we're left with 3, 5, and 6. Carolyn has to remove the 6, and she does. That leaves 3 and 5. Paul gets rid of the 3, and that leaves 5. Carolyn can't remove the 5 because there isn't a 1. So then Paul removes the 5. Okay. So Carolyn removes one number. Paul removes sometimes a few numbers, and the game ends just after Carolyn can't remove any numbers. Okay. In this example, the sum of the numbers removed by Carolyn is 4 plus 6 is 10. The sum of the numbers removed by Paul is 1, 2, 3, and 5, 11. Okay. Okay, it says they're playing a game. I suppose it's a game that doesn't have a winner? Maybe. It doesn't look like this is a strategy question. I thought, while I was starting to read this, that they're playing a game that, usually when there's a game theory question, it's something to the effect of prove that Paul can always win if you start with a prime number, or prove that Carolyn can always win after so many moves. But there's no winning condition. They're just sort of going back and forth playing around with numbers, which is fine. Playing around with numbers is great practice. There's a whole field of it called number theory. Okay, so we've got 3 questions here, A, B, and C, and yeah. Now it's the last question, so I might read all of them, but okay, just to get a sense of where we're going in case we need to build up any theory along the way. Suppose that n is 6, same sort of thing, and Carolyn removes the 2 on her first term. Determine the sum of the numbers that Carolyn removes and the sum of the numbers that Paul removes. So they're very interested in sum of numbers. I don't know why. If n is 10, so now we're reading B here. If n is 10, determine the maximum possible final sum for Carolyn. Prove that this sum is her maximum sum. That might involve some casework. Interesting. And C, if n is 14, prove that Carolyn cannot remove 7 numbers. Okay. Carolyn can't remove 7 numbers. Well, Carolyn removes 1 number each time she makes a turn, so she would have to have 7 turns. So she'd remove half the numbers. And Paul always removes a number on his turn, guaranteed. So Paul would be removing at least 1 number on each turn. So I think Carolyn would have to remove if she did get 7 numbers, she'd remove 7. Paul would have to remove 7, and so it would go Carolyn picks a number, Paul can only remove 1 number, because if he removes multiple numbers, I don't think Carolyn will be able to get her last number in. Because they alternate turns, so if Carolyn removes 7 numbers, Carolyn's had 7 turns. And that means Paul has had 6 turns, but Carolyn's not allowed to move unless Paul would be able to remove a number. Interesting. I mean, that doesn't do anything. That doesn't prove C, but it does make the remark that she has to remove 1 number each time, and so does Paul. But I don't know. I'm just thinking about C. Let's get to A. A is going to be a little easy. It's going to sort of ease us into the game. Carolyn removes a 2 at the start of her turn. Fine. So let's sort of make up a chart the way they have it. So Carolyn, Paul, Carolyn, Paul, Carolyn, Paul. Let's say removes, and then what's left. I don't need to write out my reasoning on the side. So Carolyn removes a 2. That leaves 1, 3, 4, 5, and 6. Paul removes the factors of 2 that are left. So it's 1. Okay. Now, what can Carolyn do? She can't remove 3 or 5. In fact, and I'm going to maybe make future use of this, so I'm writing down this fact so I can exploit it later. 1 is always removed by Paul on his first turn. Subsequently, prime numbers cannot be removed by Carolyn unless it's her first turn. Yeah. So nice little facts. Because she can't remove the 3 or the 5 because there's no 1 to go along with it. So we could even say that. The 1 is already gone. And that's the only other factor. And that's the condition. She is not allowed to remove a number unless Paul is then able to remove one of its factors. But the 1 is already gone. So she can't remove a 3 or 5. This is good reasoning. Can't remove 4, since 1 and 2 are gone. And those are the only other factors of 4. Therefore, she removes 6. So 6. So all of this reasoning goes into here. 6 gets removed, 3, 4, and 5. Just like before, Paul does a 3. So that's the only factor of 6 left. And once again, she can't remove a 4 or a 5. Once she can't remove a number, she'll never be able to remove that number. Nothing Paul does will change that. So no move. And so that leaves a 4 and a 5. So Paul removes a 4 and a 5. So Carolyn, in this one, removes the 2 and the 6. Carolyn's sum. There we go, nothing fancy there. 2 and the 6, and that's about it. Okie dokie. Now B part, that was, again, talking about sums. Right? If n is 10, determine Carolyn's maximum possible final sum. Prove that the sum is her maximum final sum. Okay. So, Uh, what can we do? Well, okay, so Carolyn, we start with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We want as big a sum as possible, so perhaps we want to start with some of the bigger numbers, like 10 or 9, 8. But how are we going to prove that it's as big as possible? So Paul, I'm going to say Paul always removes a number. Carolyn removes one number exactly, except on her last turn. So, can I combine these two to say something like, the game lasts at most n over 2 turns? I feel like there's something like this is true. I can't think of what it might be right now, so let's move on. But so what I'm thinking is, I think Carolyn can do at most 5. I think she can do 5. So what if she could get the top 5 here? If I could show that Carolyn can have at most 5 turns here, and I show that she actually can get all 5 of the big numbers in just the right way, I think we'll be fine. She'd have to remove the 7 first, because it's prime, and it's the only prime, so that's not a problem for us. And then I guess it would trickle down from there. There's probably a very specific way you have to do this, but yeah, okay. Let's see if we can figure this way out, and then I'll worry about she has to have at most 5 turns. But actually, so I've got this fact. Paul always removes at least one number. Carolyn removes. So let's see equal the number of numbers Carolyn removes. So Carolyn gets C turns, possibly plus 1. Gosh, I just I don't think Carolyn can't remove. Okay, let's say this. Carolyn cannot remove over half the numbers. So Carolyn removes at most n over 2. This is the floor function, by the way. It forces it to be an integer even when it's not. Just the greatest integer less than or equal to. All right, so let's reason this out. She can't remove over half the numbers. And I'm going to phrase this broadly. It'll apply for 10, but I think this might help for C part as well. Suppose she removes C which is greater than n over 2. Numbers. So she removes C numbers. Paul must always remove at least one number after she's done. And just remember, Carolyn can't remove a number. Like, the game will never end with Carolyn removing the last number, because she's not allowed to remove a number. She can't remove a number unless Paul can take a turn after her. Okay, that's a stipulation in the rules for her. Carolyn must remove one number from the list such that this number has at least one positive divisor. Then Paul makes his move by removing that positive divisor plus any of the other ones as well. So Paul removes at least C numbers 2. But combined, they remove at least 2 C numbers, but that's greater than 2 times n over 2, which is n. And that's more numbers than were there. Alright, so I phrased it this way so I don't have to worry about the sort of the end game about Carolyn. I'm not talking about number of turns they have. I'm talking about number of numbers Carolyn removes, and that avoids me having to say, well, because if I said, well, Carolyn has 7 turns, is that she removed 6 numbers and then had a turn of nothing, or she removed 7 numbers? That sort of a thing. But I phrased it this way in talking about the number of numbers she's removed. I think it's a little cleaner, and there we go. So if n is 10, she can remove at most 5 numbers. Okay, so I'm hoping this works out, but so I'll just, if I have to come back and erase this, but I'm going to say I claim she can remove 6, 7, 8, 9, 10. I feel like there's enough factors, the 10 has a 5 and everything like that, that this will work out. So I claim she can remove 6, 7, 8, 9, 10, which must be the largest sum she could get. It's the largest 5 numbers, and she can only remove at most 5 numbers. So there, that's fine. I just need to prove that she can do it. So it's a lot like 3. We think this is the answer, but we got to go ahead and show it. Alright, let's make a little chart here. Now the 7 has to go first. You don't have to explain it. You just have to say, here's the list of instructions that get her to removing these. Carolyn, Paul, Carolyn, Paul. So we need at least 5 Carolyns. Okay. So what's left over? And removes. She's got to remove the 7 first. Don't have to explain it. Don't have to talk about primes right now. And maybe my statement about primes isn't helpful. I think it might be for C part, but we'll cross that bridge when we get to it. Only one factor of 7 left, so Paul removes 1. Okay, now Carolyn needs to remove 1, and we have to limit. Paul can't remove 2 at a time. So, of 6, 8, 9, and 10, which of those has has just 1 factor left? 6 has the 2 and the 3. No, because then Paul would remove 2 and 3, and we'd run out. 8 has 2 and 4. 9 has just 3. 10 has 2 and 5. So she's got to remove the 9 next. Again, you don't have to write down this. I'm just explaining my reasoning, so you can follow along. Paul has to remove the 3. It's the only one left. Now she can go for the 6 because it's just the 2. And then that'll leave just the 5 for the 10 and the 8 and the 4. Although, I suppose you could do it in either way. So the 6 is gone, 8 and 10. Paul removes the 2, so that's 4, 5, 8, 10. Do it whatever order you like. 10 is gone. Paul removes the 5. Carolyn removes the 8, leaving just the 4. Paul removes the 4, and we're done. So that did it. And she got 5. We proved that 5 is the most she could ever pull out. And she got the biggest 5, so that's got to be the biggest sum. And we explained that. If you want to add a bit more to your explanation when you write it up, that's fine, but there we go. Alright, feeling good, feeling good. B part done, and that was actually kind of clean and nice. And it was a fun little challenge there. Can I actually get the 6, 7, 8? Because I wasn't entirely sure, but I had a hunch. I figured that it wouldn't be something completely fiddly. C part. If n is 14, prove that Carolyn cannot remove 7 numbers. Ooh, okay. So, I think we'll have to use this fact again. If she removes, she can remove at most 7 numbers, and then Paul would have to remove 1 number each time after that. So, is there a way to show that? So if she removes 7, Paul has to remove 7. It's guaranteed. We've made that comment. So if Carolyn removes, because we already said if she removes C of them, Paul removes at least C. You could restate that, or I think I didn't state it generally enough a couple pages ago. Paul removes at least 7. And therefore, Paul removes exactly 7. Because 7 plus 8 would be more than 14. So it's got to be 7 plus 7. Okay. So Carolyn takes a turn, Paul takes a turn. Carolyn takes a turn, Paul takes a turn. Okay. Let's write down the numbers and see if we can see anything. Now, we're not shooting for largest sum or anything. They're not talking about sums at all, so I don't need to focus on the last 7 numbers or anything like that. Now, primes. She can remove only 1 prime, right? There's 1 prime, 2 prime, 3. If there were... Are there enough primes to make this work out? There are 6 primes. Okay. That's pesky. Paul has to remove... Carolyn can remove 1 of these primes. Paul has to remove the others. Right? I don't know. I don't know if this is going to lead anywhere. There are 6 primes. And I've already remarked Carolyn can remove at most 1. It's fine. Maybe she doesn't remove any. Carolyn can remove at most 1. So Paul removes the other 5. So that would be 5 of Paul's turns. And so, you know, he might remove the 2 because she played the 4, or the 6 because the 3 because she played the 6, the 5 because she played the 10, the 7, 14, but 11 and 13 don't come from anywhere. So can we focus on the 11 and the 13? Consider 11 and 13. When are they removed? Paul removes at least 1 of them. when. Okay? Because maybe Carolyn comes along, she picks the 13 for her first move, and that gets rid of the 1. That's fine, but the 11 is still there, and when is the 11 going to ever be removed? So... since Carolyn removes 7... By the way, I didn't state it at the start. I'm doing a proof by contradiction. I'm going to say... assume she actually can do 7, and we'll show why this doesn't make sense. Okay? Since Carolyn removes 7, and Paul does 2, Paul must remove 1 after each of Carolyn's 7 turns. So, each number Paul removes must be a factor of some number that Carolyn removes. So what I'm arguing here is it's not going to come down to the Carolyn can't move step. It's got to be Carolyn takes 1, Paul takes 1, Carolyn takes 1, Paul takes 1, Carolyn takes 1, all the way down to the very end, and then Carolyn takes 1, Paul takes 1, and then there are no more numbers. But in that last move, if Carolyn takes 1 and Paul takes 1, then that 1 that Paul takes must be a factor of hers. Just like he took the 4 at the end of the last one, which is a factor of 8. So every number that Paul removes must be a factor of some number that Carolyn removes. But neither 11 nor 13 is a factor of some other number less than or equal to 14. Like if Paul removes the 11, what did Carolyn have to remove to make 11 the factor of that? Well, she'd have to remove something like 22 or 33. Those aren't here. So Paul can't remove 11 or 13. But by assuming Carolyn removes 7 numbers, he must. This is a contradiction. Okay? We assume Carolyn can remove 7 and show that that leads to a nonsense statement that Paul is able to remove an 11 or 13. So Carolyn cannot remove 7 numbers if n is 14. There we go. I don't know, she might be able to remove 6 or something like that, but she definitely can't remove... In fact, she probably could. She removes the 13, blah, 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 and then on her last move, it's a none, and then Paul takes the 11 and some other number that's left over. Because there'll be 2 numbers that Paul removes at the end there. And yeah, so that can be done. Alright, not so bad. So she probably does everything that she did in the n equals 10 case and then removes 14, maybe. Yeah, instead of starting with it doesn't matter. But I'm thinking she removes a 13, then she removes the, what did we say, 9, then the 6, then the 10, then the 8, and she'll probably remove the 14. Paul removes the 7 after that. Then she has a none, and it'll be 11 and 12 that Paul removes at the very end. So, that's one way. She can do 6. They didn't ask me to prove that, but I've just verbally stated that. She can actually do 6. But there we go. That's question number 4. That actually wraps up the whole Galois quite nicely. There's nothing else here. I would say it's been a good contest. I liked it. I'm eager to try the 2009, and even more eager to try the 2008 Hypatia. And if you found this one kind of easy, I would suggest you try this year's Hypatia. If you found this kind of hard, even if you are in grade 10, maybe ease off for a moment and try the 2008 Friar, just to practice your write-up and to get a handle on these sorts of questions. Okay. But that's it for me. Feel free to throw a like on the video to show that you're still interested in Galois papers or written solutions. Feel free to subscribe to be kept up to date the next time I post a Galois. And feel free to leave a comment if you had a different way to write these things up. I'm always interested to read those sorts of comments. And yeah, that's it from me. I'll see you guys in whatever video of mine you watch next. Until then, have a wonderful day.